Okay, so once again, we're talking about tangents. So let's consider any old function. There's a function f of x. And let's say I'm interested in a point P. And I would like to determine, pretend that that's not quite, let's change this up here a little bit. I don't want a horizontal line because that's a special case. So let's make it like that. So we're not going to continue. We're not going to consider this guy. We're going to consider this guy. Okay, so, and I want to come up with the slope of the tangent here. That's the tangent problem. I'd like the slope of the tangent. But the problem is, I only have one point on the tangent line. That's our problem. So what we do, I'll draw another diagram here. What we do is we allow for another point. We allow for another point to be placed farther along the curve at Q. And what we do is we calculate the slope of the secant. Now that I can do. Okay? If I think about this, if I allow this to be x, and I allow this to be another point farther along the x-axis, how far? I don't know. How about a change in x? So this will be the new point, x plus delta x. So this was a distance of delta x, whatever that might be. This is going to be a range value of f of x, and this will be a range value of f of x plus delta x. And what we do with this is that if I'm going to be talking about the slope of the secant, PQ, it's going to be delta, they'll rise over run, so delta y over delta x, and in this case it's going to be f of x plus delta x minus f of x all over top of, now it's x plus delta x plus x. So remember what's happening here. This is y2, this is y1, this is x2, and this is x1. So it's delta y over delta x. And what happens here is we get f of x plus delta x minus f of x over x. And once again, we recognize this. This is our difference quotient, right? This is the slope of a secant between any 2 points, as long as my first point is defined as x, and my second point is defined as some point farther down the x-axis at delta x. Yes? Did I add? Yeah, that should be subtract. Sorry, that's a difference. Thank you. Thank you very, very much. That is definitely a subtract because it's a difference. So what we do to try to solve this problem is we start bringing Q closer and closer and closer to P. So we move Q. And by moving Q, what you're doing is you're changing the distance between x and our new point, our new delta x. So this will be Q1, and we'll call this Q2. And then we'll move it even closer. And notice what's happening to the slope of the secants. As I keep moving Q closer and closer to P, I keep getting a secant line that is getting closer and closer and closer to the actual slope of the tangent line. So what's happening here is we're going to take the slope of the secant, p comma q, and we're going to take its limit as delta x approaches 0. We're going to allow it to get closer and closer and closer. We're going to allow this q value to get closer and closer and closer to the p value. And what that gives us is the limit as delta x approaches 0, using this notation now, of f of x plus delta x minus f of x over, oh, this was a mistake. Sorry, kids. That was a delta x. X subtract x leaves me with a delta x here. Over delta x. And this, by definition, is how we're going to come up with the slope of a tangent. Now, in certain textbooks, they're going to use delta x to represent this distance, and in certain textbooks, they're going to use h as a different variable. There's no difference. So if you see this, oh, shoot. That's just h. There is no difference between the top one and the bottom one. Notice this one has delta x, delta x, delta x. This one has h, h, and h. It's just a difference in the variables that we use. I'm going to pause the video there and be right back.